We did this. So for a few exercises where we didn't go through.
Excuse me.
Yeah.
Can you tell us when are the results coming out?
Well, I'll try and get them done as soon as possible. But,
You're not part of the strike then, so.
Pardon?
Not part of the strike, so that's good.
What strike?
There's a strike going on.
I probably should be on strike. It seems a bit ridiculous, you know. People in my situation going on strike, you know, we're paid quite well. We have a lot of flexibility. Find a job somewhere else quite easily.
But what about your pension?
They are screwing my pension.
They are.
But you know, if I get a job in the States at some point anyway, then I'm screwing my own pension. So,
Yeah, have a sip.
I thought you were
What?
going to
Get a sip. Self-invested pension.
we kind of
What? Me?
Well, we didn't do
Chris.
did
He
we?
has one. Do you not actually need to transfer more? We get the pension and need to transfer it before I lose it.
For that, I think probably also because of the tax and how hard it works, we made a margin a lot better.
So we had this question, I don't think we went through this. So we had Q is 1 minus P, entry cost of zero marginal cost, some entry cost. And there was a, let's see that. And we had a question in the lecture about the welfare optimal number of firms. Which is, I don't know, it's a bit late for Corno revision, but we'll go through it quickly. Okay, so profits here are going to be, you did a question like this in the exam, right? Price times quantity. Pardon?
A couple of them were all
I
right.
think it was just lengthy minimisation of it. I don't think
let's
it's
look at some of the
Stop the exam.
it just took time to.
We need PR.
Yeah, okay, so let's, so Q is 1 minus P, so P is 1 minus Q. That's the easy way to work. Okay, so profits are little quantity times 1 minus big quantity. Okay. So this is Corno, yeah, so this is a Corno entry game, but we're solving for the second stage first, okay? So we've done this a million times, so naught is d pi d little q, which is 1 minus q minus little q. So derivative of this is 1 times that, plus this times derivative of this, which is minus 1. Pardon? So, so this is true, there should be some QIs, I suppose. This is true for firm I, pi I as well, yeah. So when we add all of the first order conditions together, you get n minus nq minus q. Okay, so this is right, isn't it? Yeah.
Yeah, fact.
Sorry, I'm very tired from the slides. I'm not going to be completely. Yeah, I know. Just checking.
He knows how to do maths.
So this is n minus n plus 1 times q. Okay, so q is equal to n over n plus 1. Okay, so that's big Q, so little q is going to be 1 over n plus 1. Okay, and profits are going to be 1 over n plus 1 times 1 minus n over n plus 1. So how do we simplify this fraction? What's this thing equal?
That's equal to n plus 1 over n plus 1. N plus 1. You want the denominator on both.
Yeah, go on.
1 divided by n plus 1.
Yeah, exactly. So 1 is n plus 1 divided by n plus 1. So this is n plus 1 over n plus 1 minus n over n plus 1, which is 1 over n plus 1. Okay. So this is 1 over n plus 1 all squared. Okay, so in equilibrium, firms carry on entering until the cost of entry is equal to post-entry profits. So F is 1 over n plus 1 all squared. Okay, so square root of F is equal to 1 over n plus 1. 1 over square root of F is equal to n plus 1. N is equal to 1 over square root of F minus 1. Okay, we did this in the class. Okay, so that's what happens under laissez-faire. Okay, letting the market do what it wants. So we want to know what welfare is. So think about welfare. Here's price. Here's quantity. This is 1. This is 1. And we've got some big quantity. There. Got 0 marginal cost. So welfare is all of this area. Can't see. Okay, so this is a trapezium. This side is 1. If this is q, then this is 1 minus q. Okay, so welfare is going to be q times half of 1 and 1 minus q. Yeah, you could do it as, alternatively you can think about if this is a square, which is q squared, and this is a triangle, which is 1 minus q squared divided by 2. So this is so this is q times 1 minus q over 2. So this is q times minus q squared over 2. Okay, so q minus q squared over 2, that's another way of thinking about this area. Remember, this distance is q. So a big square like that would be area q. And then you just have to take off this triangle. What's the area of that triangle? Well, this is q. Okay, so that must be q as well because it's an equilateral triangle. So this triangle here is q squared. Q squared over 2. Okay. So it's kind of the geometric interpretation of the answer. So welfare is q minus q squared over 2. Q is n over n plus 1. So welfare is n over n plus 1. Minus n plus 1 all squared. Okay. So just to show you what I was talking about before, this is Q. Think about all of this area. Okay, so if this length is Q, then this length is Q as well because this is a 45-degree line. Okay, so this triangle here is the Q squared over 2. Okay, so it's Q minus Q squared over 2. And here we've got some expression for welfare. Seem to remember we got a neater expression last time we looked at this, but maybe we didn't get this one.
Oh, we got actually for 1 over n squared or something like that.
Oh, because we substituted in for the optimal n. Okay, so this is welfare. Let me do it a better way. So, sorry. So we know what Q is in terms of n, right? Q is n over n plus 1. We know that n satisfies this equation, okay? So n is 1 over root f minus 1. So let's just plug in to work out what Q is. Okay, so Q is n over n plus 1. N is 1 over root f minus 1. Okay, so this is 1 over root f minus 1 plus 1. Okay, so minus 1 plus 1 cancels out. So this is 1 over root f minus 1 divided by 1 over root f. Okay, so let's times top and bottom. You see? Let's times top and bottom by square root f. Okay, so this becomes 1, this becomes root f, this becomes 1. So this is 1 minus root f. Okay, that's a bit nicer. Okay, then we're going to plug that into welfare. So welfare is q minus q squared over 2, which is 1 minus root f minus 1 root f squared. So multiply out the brackets, maybe simplify it a little bit, 1 minus root f. So this is minus 1, let's make it all over 2. So multiplying out the brackets, we get a 1, we get a minus 2 root f, and then we get a plus root f squared, okay, which is plus f. Okay, so 2 root f divided by 2 is just root f, minus minus is a plus. Okay, so this minus root f and this term here is going to cancel out. And we've got 1 minus a half, so this is going to be a half minus f divided by 2. Does that make sense? So, yeah, we should do some Kreps-Scheinkman stuff. So, and then the other question asked was what the welfare optimal number of firms was. Okay. So oops. So what we've got here is the good bit of welfare. So we've got the welfare from the entry stage, but remember that in welfare you also have to include the cost of entry, okay, because that's wasted resources. So really, let's call this welfare 2 for welfare from period 2. So actual welfare is welfare from the second period minus n times the number of entry costs. I made a mistake last time. Half minus f over 2 minus n was equal to 1 over root x minus 1 over root x. So total welfare is welfare from the second stage minus n times the number of entry costs, okay, because the entry cost is just pure wastage. So this is what we got for second stage welfare, and then we're just subtracting n times the entry cost. Okay, so let's think about the welfare optimal number of firms. Okay, so welfare. So its overall welfare was q minus q squared over 2 minus n times the number of firms. Okay, and let's write it in terms of n. So this is n over n plus 1 minus n over n plus 1 all squared times a half minus n times n. So that's just an expression in n, right? So to find the welfare optimal number of firms, we just differentiate that expression with respect to n. Okay, it's not particularly nice, clearly. So at a maximum, the derivative of welfare with respect to n should be 0. So taking it one term at a time. So derivative of n over n plus 1. Well, remember, derivative of u over v is u dash v minus v dash u over v squared. Okay, so this is u dashed is 1 minus v dash minus u dash v, so 1 times v, which is n plus 1. U dash v minus v dash u, so v dashed is 1 again, u is n, so n plus 1 minus n, all over v squared, n plus 1 squared. Okay. To differentiate this term, we're going to use the chain rule. Okay, so the derivative of x squared is 2x. So to start with, we're going to have the derivative of the outside, which is just going to be the half and the 2 are going to cancel out. So this is just going to be n over n plus 1. So that's the derivative of the outside, then we do the derivative of the inside with respect to n. Okay, the inside is just what we had before. Okay, 1 over n plus 1 all squared. Then the derivative of this bit here is just going to be minus f. Are you happy with my algebra? There's a fairly high chance of me making mistakes at the moment, so do tell me if I do something stupid. So we've got, so let's simplify this a bit, because at the moment it's messy. So this term here is over n plus 1 cubed, right? So let's make this over, so this is 1, n minus n is 1. So let's make this over n plus 1 cubed, so this is n plus 1 over n plus 1 cubed. So we've got n plus 1 over n plus 1 cubed minus n over n plus 1 cubed. Okay, so that's going to be 1 over n plus 1 cubed. So 1 over n plus 1 cubed minus f. Okay, so f must be equal to 1 over n plus 1 cubed. 1 over f must be equal to n plus 1 cubed. Okay, so n plus 1 is equal to 1 over the cube root of f. Okay, that's just the same as 1 over f to the power of 1/3. Okay, if you're more comfortable. This notation means cube root, but if you're more comfortable with this notation. Okay, so n is equal to 1 over cube root of f minus 1. Okay, whereas what we got, yeah, so the point of all this nonsense was comparing this number and this number. Okay, so this is what you got under. This is, where is that? Up there. This is what you got over laissez-faire, so 1 over square root of f. The optimal number was 1 over square root of f minus 1. Optimal number was 1 over cube root of f minus 1. The profits are always less than 1 here, right? The maximum profits can be as a half. Okay, if all welfare was going to profits, then profits would be a half, right? So the entry cost certainly has to be less than 1. Okay, so with f less than 1, which is going to be bigger, 1 over square root f or 1 over cube root f? Yeah. So f is less than 1. If you think about what square root and cube root look like, okay, here's 1. This is, so the square root of 1 is 1, right? So So here's square root f, looks something like that. And cube root f, cube root is always bigger for numbers smaller than 1. Okay, so you know so cube root f looks more like this. Okay, so they cross at 1. So cube root f is always higher. So 1 over cube root is always smaller. You know, you can just convince yourself this on your calculator if you want.
Cube root of half.
Can you do the second thing?
Cube root of an 8 is a half.
Oh, cube root. No,
It's the other way around.
Other way around.
So-
You know, you can show it for me.
It's just like if you just get your calculator.
I'm definitely going to have to.
Okay, so that was just a quick check, but under Corno there's too much entry. Okay, in the lecture we proved it quite generally, but there's always too much entry. Okay, this was a special case which showing there was too much entry in the Corno.
My brain hurts already.
So that's right.
Okay, and we ought to do some of this Kreps-Scheinkman stuff because we're all quite bored of Corno, really, so I guess, yeah. So,
No, I don't think we did.
pardon?
I don't think we got it. You've seen this. I don't think
I
we've seen it.
I don't. We would have laughed about that name already.
Yeah, you did. We did all this stuff about rationing. Don't you remember this two-stage game?
Must have been asleep there.
Because I said it wasn't going to be on the test. You clearly turned off. And
Yeah, we didn't get very far down.
no, we finished this lecture.
No, we didn't.
We did.
Apart from the M.
I'm sure we did take.
Yeah, we finished this lecture. We didn't start the next one,
Oh yeah.
but we at least finished this one.
Yeah.
We're not so far behind. You know, we did all this stuff about rationing. didn't we?
Yeah, I remember that Alex.
Lecture
Yeah.
4 we didn't
I
start.
get that bit.
Yeah, we did that.
And then,
Yeah, we did that. And then we did that.
Yeah, we
we
did
did
that.
finish it.
We did this.
Yeah.
Yeah.
Yeah, you remember this?
Yeah.
Yeah.
Okay, so we're as an exercise on that
I
stuff.
think you got to the summary bit.
Isn't that the end?
No, if you go.
We're as an exercise. Okay, well let's go through this anyway. It doesn't matter if you haven't tried it. You had other things to do, I guess, with the test. It was always unlikely you were going to do it. Okay, so remember what these games were? In the first stage, firms chose a maximum capacity. Okay, and in the second stage, it was Bertrand competition, but it was Bertrand competition up to that capacity. They couldn't produce more than that capacity. If demand was higher than they could produce, then some consumers were going to be rationed. Okay, and we looked at the case when consumers were rationed with proportional rationing. With efficient rationing. And this was looking at the case when consumers were rationed with proportional rationing. So we're just going to go through pretty much the same steps as what we did before. Okay, so the demand curve was Q of P equals 1 minus P. Okay. And what we had to prove was that the same price, okay, we had to prove that P star equals 1 minus Q1 bar minus Q2 bar was an equilibrium in the second stage game. As long as Q1 bar was less than a quarter and Q2 bar was less than a quarter. So that was what we were trying to prove. So we're just looking at the second stage game. So it's Bertrand competition. two firms have those capacity constraints. We're going to show that this is indeed a Nash equilibrium. Okay, so to show something's a Nash equilibrium, you want to check that no one wants to deviate. Okay, so people are either going to deviate up or down. So the first thing to check is, well, what happens if they deviate to a lower price? Okay, so at this price P star, what's the quantity going to be? So if the price was equal to P star, what quantity in total would be being produced?
Yes, and minus Q1 minus Q2. Oh, it's not minus.
Yeah,
Yeah.
so it's what you Q1 bar plus Q2 bar, right? Yeah? Okay, so if the price was that, then just from substituting the price into the demand curve, right? So Q of P is, so Q of P star is 1 minus P star, okay, which is 1 minus brackets open, 1 minus Q1 bar minus Q2 bar. Okay, 1 minus, those cancel, so that's just Q1 bar plus. Okay, so if that was the price, then the total quantity produced is the sum of the two capacitors. Okay, so both firms are producing the maximum they can possibly produce. If one firm reduces its price, it can't produce anymore. Okay, remember profits are going to be price times quantity. Price has gone down, quantity can't go up, so there's no way that profits can go up. Okay, price has gone down, quantity stays the same. So neither firm wants to reduce their price because they're already producing the most they can possibly produce. So there's no profitable deviation downwards for these firms. Okay, so we just have to check whether there's a profitable deviation upwards. So suppose firm 2 deviates to choosing a higher price. Okay, so let's suppose that so firm 2 chooses some price P2 which is bigger than P star. Okay. Well, if that's the price they set, then firm 1 is then cheaper than firm 2. All of the demand is going to go to firm 1 to start with, but then some people are going to be rationed. Okay, firm 1 can't sell any more units. So the demand curve facing the higher price firm is going to be the rationed demand curve. Okay. In the lecture we did it with efficient rationings, and this question was about doing it with proportional rationing. So with proportional rationing, the residual demand curve was given by Q of P2 times Q P1 minus Q1 bar over Q P1. So that's what we derived in the lecture. Okay, this was the residual demand curve facing the high price firm under proportional rationing. Okay, so if you like, it's the original demand curve scaled down a bit. Okay, so here's the original demand curve, and it's just some multiple of that original demand curve. So if this is what demand is, what are profits going to be from deviating? Well, that's what we're trying to show, yeah?
Scale, effectively small. The scale.
Yeah.
So the price increase.
Yeah, it's very smart. Yeah, that's probably, Is that? Well, let's go through it anyway, but I think that's the right idea. So, if this is, demand is, if they go to a higher price, demand is just scaled down. So, kind of almost immediately profits have to be lower.
But the price is higher.
But the price is higher.
So kind of.
Yeah. Yeah, but the thing is that they're scaled down. So if you like, the demand curve jumps downwards once their price goes above a certain point. So demand has jumped downwards by some proportion, and price has only increased continuously. So there's a jump down on one side and a continuous increase on the other side. but let's go through the maths and it'll be clearer. Okay, so profits are always price times quantity, right? So profits for firm 2 is P2 times QP2. So QP1, firm 1 is still choosing the optimal price. Okay, so QP1 we already showed before was Q1 bar plus Q2 bar. Okay, minus Q1 bar, all divided by Q1 bar plus Q2 bar. Okay, so this simplifies down a bit. It's P2 times 1 minus P2, just using the definition of the demand curve, times Q2 bar over Q1 bar plus Q2 bar. So this is their profits if they choose a price higher than P star. Okay. Okay, without doing any maths, at what price is this maximised? No differentiation required.
0? No.
Yeah.
No. If it's 1, it's 0.
No, it's
If
one,
it's
yeah,
0,
zero,
it's
it's
0.
Half, yeah, thank you. So, yeah, this is just a quadratic, it's 0, 0 and 1, so it must be maximised to half, okay? So you don't need to differentiate for these things. So if a firm had the choice of what price to choose, with a price bigger than P star, it would like to choose a price of a half. So the question is whether P star is bigger or less than a half. Okay, that's what's going to be important there. So here's profits. Here's 0. Here's 1. Let me just do a dotted line. So that's what profits are going to look like. And this is the line for prices bigger than P star. So if P star is on the right of a half, then firms will never want to increase their price. Okay, if P star was on the left of a half, then firms would want to increase their price. Okay, so what matters for whether or not a firm will want to deviate is just whether P star is bigger than or less than a half. Okay. Well, we said to start with that Q1 bar was less than a quarter and Q2 bar was less than a quarter. So the sum of Q1 bar and Q2 bar must be less than a half. So P star must be bigger than a half. Okay? So P star is bigger than a half, and their profits look like I've drawn in this diagram. Okay? They would like to lower their price from this point, not increase it. Okay, but we've already said that if they lower their price, they're worse off. So they certainly don't want to increase their price. Does that make sense? Okay, so it's slightly strange because if they increase their price, they face a different demand curve to the one they face when they decrease their price. So, you know, they can never get to this point. Okay, because what actually happens is when they start decreasing their price below P star, their profits just decline linearly. You know, so their profit function actually looks like this. Okay, they have some linear decline, and then a decline from this. These are the other profit function. Okay, so they don't want to decrease, they don't want to increase. So that's it. You've proven that it's a maximum, that it's a Nash equilibrium. Okay. Neither firm wants to deviate up or down. Yeah, so these conditions, so we just assumed these conditions. So we said, suppose it was the case that in the first period, they'd chosen quantities both less than a quarter. Okay, so remember in the efficient rationing case, it was quantities less than a third. Okay, and under efficient rationing, you can show that they actually want to choose quantities less than a third. Under proportional rationing, they don't want to choose quantities less than a quarter. Okay, so this is why under proportional rationing you don't get the Corno outcome coming out. Okay, it's harder to achieve. Under proportional rationing, firms have more incentive to invest in the first period, and in the second period, in the second period, the condition on getting the Corno output is tighter. So if the condition we started with wasn't satisfied, maybe this is a better way to think about it. So suppose that these quantities chosen in the first period were bigger than a quarter. Okay, then P star would be less than a half. Okay, and then both firms would have an incentive in the second period to increase their price. Okay, so the second period they would want to deviate. And in order to stop them,
They're able to deviate up to a half.
they want. So they both want to deviate up to a half.
Which
Okay.
is how you get to a quarter being cut-off point.
Well, the quarter is a cut-off point. Yeah, I think it's 2 effects. Yeah. But if they're just producing if they're selling a fixed price of a half in the second period, okay, then that changes their decision about how much investment they want to do in the first period, right? If you know that you're going to set a price of a half in the second period, then you want to do as much investment as possible in the first period, right? If your price is kind of fixed in the second period, then your profits are just quantity times the price. So as long as the cost of investment in quantity is less than that price, you want to do lots of investment in the first period. Okay. So the equilibrium of this game would have lots of investment in the first period, and then both firms setting a price of a half in the second period. Okay, and for some excerpts from the book, did anyone have a go at this? 6.8, question 2. No? Anyone?
Oh. Question 2.
Sounds like a set.
What's this now?
Have we done this before?
Have we done this?
I've got a feeling we've done this.
Maybe we did the last.
No, we did.